can actually do it. Maybe that would be more meaningful than talk about like machine learning or anything like this.
No. Just not. It's not mutually exclusive. So
sure.
Can you see maybe some simple idea? Imagine we want to approximate this problem.
Right. Okay. So like okay. Here is a very simple algorithm that actually works and gives decent results. Suppose that okay, so let's not do Euclidean distance. Let's talk about Hamming distance. It's much simpler to think about.
Yeah.
So okay. So suppose that can I actually share some overlay screen where I would type some LaTeX? I think that would be easier actually for me to kind of emulate it as a whiteboard. Let's try and see what happens.
Yeah. It doesn't work.
No, because I haven't shared yet. How about now? Do you see anything?
We see
it's starting. Yes.
Oh,
okay.
Very good.
Great.
Yeah. Wow.
Okay, so how can we do something in the Hamming distance? So suppose we have some set of points that we want to pre-process.
In a Boolean cube.
Yeah, in the Boolean cube in d dimensions, and the size of it is n. So then, okay. Then the idea is very simple. So what we would like intuitively? So we would like intuitively to do some kind of matching, but it's not exact, right? Because we don't know. Like, for example, if for a query we knew that. So let's say that we receive a query also from 0, 1 to d. Then, like if we knew that in P there is a point that is exactly equal to Q, then this problem is trivial. You can just use a hash table, right? But we can't do that because, like, a priori we don't know if the closest guy is equal to Q. But what you can do is kind of like reduce approximate matching to exact matching by sampling coordinates. So that's the main idea. And so here's how.
Can you please make the letters larger, something like 2 times larger?
That's a great question. I guess I could.
Huge.
Yes.
I think
like this?
Oh, good. Good.
This is better? Okay. Awesome.
So you just delete randomly half of coordinates and hope that all the errors are gone.
Exactly. I mean, so let's actually analyze this. It's very like it's not that bad to analyze. So it's more convenient to sample coordinates with replacement. So basically, we can choose the same coordinate several times. It doesn't matter for the algorithm, but it's slightly more convenient for the analysis. So basically, the algorithm is the following. Let's choose. Let's sample uniformly. K coordinates
out of
with replacement. Yeah, so we can include one coordinate several times. I mean, not sure why we would want that, but like, why not? Okay, good. So great. So okay, so now let's understand what's going on. Okay. First of all, I should have started with this. So as Sasha formulated the problem, we just want to find in P approximately closest point. So it's a little bit more convenient to work with the decision version of the problem. Actually, it's like in the case of Hamming distance, it's very easy to reduce to this decision problem. And the decision problem is the following. Suppose that, so basically we have a promise. Basically, our database is within distance R from the query. So basically, there is always an answer within distance R, and we know this R from the beginning, and we will use it in our data structure. And the goal is to return a point within C times R, where C is our approximation. So that's the decision version. And in case of Hamming distance, it's very easy to reduce optimization version, like Sasha introduced, to decision version. Yeah, basically because there are only D possible values of R. So we can build data structure for every R and just basically query all of them. And that works. So for Euclidean case, you can still do this reduction to decision version, but it's more like it's like more delicate. So it needs some work. And in fact, it's a paper how to do it. Let's not worry about it. Let's just think about the Hamming case for now. So, okay, so basically we want to solve this decision problem, and we sample k coordinates with replacement. So what's happening? So what do we do after we sample? So we sample, and then we like basically okay. So then let's call this set of coordinates multiset. Let's call it S. So it's kind of a multi-subset of numbers from 1 to D. Okay, so then what do we do? So then we find all database points that exactly match the query on this subset of coordinates.
Yeah,
so this can be...
Coordinates should not be very big because a probability to be different is R divided by D. So we should not have much more than D over R coordinates. Yeah, something like this. Yes. So there is a tension. If you include too many coordinates, then you will cut out your nearest neighbor or near neighbor. If you will include too few coordinates, lots of garbage will match your query, and you are in trouble. So that like we need a compromise. So let's do the analysis. It's pretty easy. So then what do we do? So we find all such P that match query on this subset of coordinates, and then we just go through them until we find something within distance C times R. As soon as we found something like this, we stop. So that's the whole algorithm. Mm-hmm. So how do we analyze this? So so let's first start with the following observation. So it's kind of like claim or lemma or whatever you call it. So expected time this takes is n times something small. So what does this claim mean? It means that first of all, how much time this process takes? First of all, we need to compute some hash function, basically find the bucket where the points that match Q on S lie. So that takes time, something like D. So we basically factors like D we kind of neglect in this. So we kind of assume that D is not too large, and factors like poly D we are okay with. So then the interesting part. We have these points that match our query on this set of coordinates, and we stop as soon as we find something close. So potentially this set can be huge. So in principle, for example, if k equals to 0, then this set is everything, right? And we need to say that so maybe this set is somewhat large, but at least we will stop quickly. But how do we know that we will stop quickly? We can guarantee that we will stop quickly by saying that there are not too many points that are further than CR that match our query. So basically, the number of times we might probe a point and not stop if it's far, right? But what's the probability that how many points in expectation, how many far points in expectation will match the query? That's exactly this number. It's like n times 1 minus CR over D to the power k, right? No, I understand. It's smaller than 1 or what? So we will make it 1. We will. Well, yeah. The second thing is smaller than 1. We will make the overall product around 1. So that would be the optimal setting of parameters. But let's not worry.
It's smaller than n. Something is.
Yeah. So it's exactly smaller than n. That's the whole point. So it's expected time of the query. Okay. Yeah. So for example, again, like if k equals to 0, then this is n, because we might need to scan everything. So there is no other way. As you increase k, this becomes better and better. But later we will see that it has some annoying consequences that we don't want to set k to be too large. So okay, so this is the first claim, and then the interesting second claim is that what's the probability that we will encounter, so what's the probability that we will return something? So that's like not very clear, because we don't know how many points are within the ball of radius CR, and also we don't know what's the distribution of distances there. But what we know is that there is at least one close point. So probability that we will succeed is at least the probability. So it's actually like a not entirely trivial logical step, even though it's like formally simple. So probability of success.
So for probability of success, we rely only on the optimal point.
Well, yeah, but so okay. Here is the thing. We rely on the optimal point in the following sense: if optimal point matches the query, then we will return something. But it's not necessarily the case that we return this close point. It's just like we will not fail, right? So probability of success is at least 1 minus r over d to the power of k. So that's exactly the proof of it is what I've just said. So if close point that we are guaranteed to have matches the query, then there is no way we fail, because we will not exhaust all the matched points and say that we haven't found anything, because somewhere in this list there will be this close guy, but it's not necessarily the case that we will return it. So that's exactly the trade-off. So on one hand, if you set k to be too large, then the expected time is good, but probability of success will be very small, so we will need to repeat this whole process many times. So that's exactly the tension here, and it turns out that the optimal way to set parameters, I'm not gonna...
Okay, I think I see, now we see the main idea, that C should be large enough so that 1 minus C of R over D is small 1 minus R over D.
So let me just say that one thing. Let me just say that if you set this expected time to be around 1, then the probability of success would be something like n to minus 1 over c. In the worst case over all possible choices of r. Basically for small r. Basically for small r, you can just use Taylor expansion here and kind of like see what's happening. And so you need to repeat this whole process n to 1 over c times. So the overall query time would be precisely something like n to 1 over c times poly d, maybe times d. And that's the whole thing. So basically, like that's a very good result. It's not the best you can do for Hamming space, but it's close to the best you can do. In the worst case,
if you have the edit distance, it's also you can do something like this or not?
No, you cannot. So for edit distance, the situation is pretty unsatisfactory. So the best we know how to do for edit distance is just embed edit distance into Hamming space pretty much, and just use this algorithm. And this embedding, it's I tried to understand it like many times. I was never able to, and my conjecture is that there are like 0 people in this on this planet that currently understand it, including the authors of that paper that wrote it. So that's
for example, Google definitely does Google definitely when suggests something. I ask for blah blah blah, and they suggest that probably you meant ha ha ha. So what do they do for this? They have some problem like this, I guess.
Actually, that's a good question. So I've heard, I never worked with edit distance myself, but I've heard that there are some like heuristic So it's maybe what they can do is they can do some kind of shingling. So they basically take a string, then like consider all the windows in this string, and then consider basically characters in these windows as some kind of like okay. So my conjecture would be that they do some kind of embedding into something like Hamming distance, but heuristic. Not that doesn't work in the worst case.
Like something like this.
Yes, but again, like I don't know the details, and I would not be comfortable speculating in the sense that I might just say something stupid or wrong. Or like, yeah.
No, it's secret. It's much worse. But there is no people who work for Yandex or Google in the room who can explain.
So I know who knows these things. Actually, like Kostya Makarichev, he had a project on. They even have a paper about this. They were doing this clustering of DNA sequences, and there precisely the edit distance is the right measure. And I think he specifically came up with some heuristic way to reduce edit distance to something like Hamming distance. So he's the right guy to ask, and there is a paper that we can even look up.
And for Google search, do I understand correctly that there is also not Google search, not correction? There is another thing. If you ask for something, then somebody constructs some vector out of this, and then search for the close things in some space.
I mean, that's almost certainly true. That's what's called word embedding, and again, not only Google does, everyone does that. So that's a way to kind of like capture semantic similarity between words. And again, like the details can be very different, but the basic idea is very simple. So the way to do something like this is to take basically all the text that you can find, and then so how do you specifically construct the vectors? That's a delicate question, but basically the idea is you should assign to words close vectors if these words occur in similar contexts commonly. So basically, at least one old algorithm that actually works still okay was to build some big matrix, so kind of like co-occurrence matrix. Basically, rows of this matrix are like all possible words, and columns of this matrix are some kind of like context. And by context, we just mean like window of words with like one wildcard, like one missing word. And in this matrix, you kind of put what's the probability to see this word in this context. And then vectors can be obtained by doing some kind of like SVD or like low rank approximation of this matrix.
Yeah. And then when you are translated, you use some near neighbors, but not with this Hamming distance approach, but with some other which probably...
Right. So that allows you, yes. So you can do nearest neighbor search in this semantic space, so to say, and retrieve similar words or similar documents. That's definitely one valid application of nearest neighbors. For example, that's what Bing does, and that's public information even, because I think they wrote a paper about this. And that's what Bing does for image search, not for text search, but for image search. So they also like encode images as some kind of vectors in like that try to capture semantic similarity, and then they just use certain nearest neighbor algorithm.
Another class of nearest neighbor algorithm. So we can maybe switch to this class and to your presentation if there are no other questions on general about nearest neighbors.
No, I have a question, if I may. It's Grigory.
Yeah. Okay. So what is
it? Can you hear me?
Not very well, but we will try.
Okay, thank you. First, the remark about embedding of edit distance or Razenштейn distance to Hamming speeds. There is no exact embedding, and it's clear why. Because different points have a different sphere in the Razenштейn method, a very different by size. Just think about all zero vectors, and you have deletion. You will always get the zero vector. So a very small.
If somebody hears the comment, Could you repeat, because I don't hear anything really.
Okay, so sorry, that's probably my microphone, and I don't know how to make it better.
But actually now it's almost incomprehensible. So,
Yeah,
I think there is probably technical obstacle. I see two copies of Grigory Kabatiansky. Maybe if we kill one of them, then the sound will be better.
okay. So
no, it's even worse. One of the copies was just
The only thing I understood is that he was trying to explain why there is no embedding from edit distance to Hamming distance. But I can make my statement more precise, and then there will be no counterexamples. So that much I can say.
We should have muted the other one, so because the other one is only with headphone.
Can we restore the first one?
Maybe yeah, can. I certainly cannot. I guess
no, I cannot. There is no button like this. Maybe they can reconnect. I don't know. That's unfortunate. Okay, so meanwhile, maybe I can give a comment on this. So when I said embedding into Hamming distance, I meant the following. So literally, there is an embedding from edit distance to L1 space. So by L1 space, I mean just RD equipped with L1 norm. And then there is an embedding from L1 to Hamming space. So it's not like faithful embedding in the usual, like by Lipschitz sense, but it's an embedding that is good enough for nearest neighbor search. So that's all I meant.
Yeah. Okay, you can try to download the presentation meanwhile, because.
Well, okay, let me switch to presentation, and then
It doesn't need the.
Okay.
Пока это самое. Андрей, у меня к вам технический вопрос.
Да.
Я поставил на запись, и...
Да, запись происходит.
А где она будет вообще?
Я потом могу прислать ссылку.
А если я выключу запись, запись выключится?
Ну, наверное.
А если я выйду вообще?
Я думаю, что вы можете выйти, а запись продолжится.
Ага, тогда я выйду.
Потом бы это хорошо было выложить на это.
Ну да. Я просто тут тоже в 2 экземплярах. Я хочу один свой экземпляр закрыть.
Да.
Okay, so let's start, and we can return to. Yeah, right. So okay, so basically, Sasha motivated the problem. Sasha introduced the problem very well, and I gave some motivations. But at the end of the day, okay, so first of all, this is based on joint work with a bunch of great people, like Yihe Dong. She was AI resident at Microsoft Research, and we worked with her when she was there. Piotr Indik from MIT, who was my advisor, and we still work with him a lot. And Tal Wagner, who is, I think now, for some weird reason.
Yeah, okay, better.
Okay, now it's better, yeah. So, and with Tal Wagner, who is also Piotr's student, he just graduated, and he will start a postdoc in our group next fall, if there will be such a thing as next fall, or our group, or postdoc, or something like this. So this really, okay, so basically in short, we use supervised learning for nearest neighbor search, but really, like, my talk will almost have nothing to do with data structures. So basically, I will very quickly just tell you, okay, here is a geometric problem, and we will be solving it using supervised learning. So it really, geometric problem. By geometric problem, I don't mean original data structure problem. I just mean certain very concrete geometric optimization problem that I would want to solve. And basically, this example with Hamming distance that I've given you, it already kind of introduces the primitive that we would like to obtain. So it's called locality-sensitive hashing. There are some other names. It doesn't matter. So the point is, we would like some space partition So in the case of Hamming distance, the space partition was just like, let's take a random subcube of our cube, and partition would be just, you know, if we sample k coordinates, partition have 2 to k parts, right, in a trivial way. So we would like to find partitions of our space. So in the case of this, in the Hamming case, it was the cube. In the case of this talk, I will talk mostly about just Euclidean space. So these partitions should respect nearest neighbor structure. So basically, close points should end up in the same part, and far points should end up in different parts. So basically, my talk will be mostly not about data structures, but about finding such partitions using certain learning tools. And basically,
in final algorithm, you will have several partitions.
Right. So basically, this talk doesn't talk how to construct several partitions. In particular, my partitions will be deterministic, and basically, there will be no such thing as, like, you know, we construct a random partition and then we sample independently several times. That I don't know how to do. Actually, that's a great open problem. So my talk will be just about like single deterministic partition. It is. You would not be able to, like, you know, build directly data structure from several of these, but I will give you at least one such scenario where such single deterministic partition is still useful. But in any case, like, forget even about data structures. So the nice thing about this result that I like a lot personally is that in my mind, learning here falls out inevitably. So it's not like, you know, we were smart and we used learning to solve this problem. It's like learning arose naturally, so we just had to use it in some sense, as you will hopefully see if we get to it. So that basically this slide is just repeating what I've just said. So like if you don't understand the data structure question, like, forget about it. It's completely irrelevant. So really, this question is about finding certain partitions of d-dimensional space that are in a certain way nearest neighbor friendly. And informally, what it means is that if you have a query point and it falls into some part, then its several closest neighbors should also be in the same part, or most of them should be in the same part. And basically, our algorithm will be very simple. It's a combination of graph partitioning and supervised learning. And it's a completely black box reduction in the sense that you can use for graph partitioning whatever you want. You can use like your favorite theoretically sound method, like spectral partitioning, or like solve some linear program or whatever. Or you can use any heuristic that you like. Anything would work well. Well, and not any, like the better partition you obtain, the better it works. And then for supervised learning, you can also use whatever approach you want. You can use linear models, neural networks, whatever thing machine learning practitioners will invent tomorrow. You can just plug it back into our algorithm. Yeah, and that performs certain other methods. Again, maybe it's not so important now. Later we will talk more about possible alternatives. Yeah, okay, so all of you know what metric spaces and norm spaces are, so these slides are for non-mathematicians. But
sorry, we still see. I see still the title slide.
Oh, you do?
Yeah, for sure.
Oh yeah,
now it's good. Yeah.
Oh wow, that's actually not good, because I was hoping to be in the presentation mode. Because okay, you know, it's fine. Okay, so this slide is like incomprehensible mess for you now, but what this slide is supposed to explain is to explain for non-mathematicians difference between metrics and norms. But all of you know what norm space is. I don't need to introduce it, I hope.
Yeah.
So okay, good. So let me just repeat what is the problem that we are solving. So yeah, so we basically solve decision version of this problem, as I've already explained for the Hamming case. When we have certain distance threshold R and we want to find a point within this distance, and for the exact case in high dimensions, basically you can do more or less like one of the two things: either compute the answer naively, so scan through all the points, or in some sense, like store all possible answers. So for each possible query, you pre-compute the best answer. Of course, literally we can't do that because query can be any point in RD, but we can, after appropriate discretization, this can be done with like exponential in D space. So more or less, like nothing else is known. And moreover, if you believe things like strong exponential time hypothesis, you cannot do better than both of these at the same time. So basically, if your query time is sublinear in n, then you must use exponential in D space. So that's like, actually, it's a very simple proof. It's a simple reduction from SAT to nearest neighbor.
It will be your next talk. Just let's go now for.
Sure, I'm not a huge. I mean, like it's not okay. I'd rather not give this talk, but sure. Okay, so it's not. Yeah. So that's why people study approximate version of this problem, and that's exactly the problem that I've already talked about for the Hamming case, when our promise is we have something close, but we're okay returning something a bit further. Okay, and let me also say that in practice, the situation is a little bit different. So that's actually interesting because theory and practice model this problem in a little bit different way. And at the same time, similar algorithms end up being useful for both. So in practice, we don't want approximate answers. We actually want exact nearest neighbors. Because usually, like even 2 approximation is way too much. But at the same time, we do not have a worst case distribution of points. So we usually have something like on this picture. So that's exactly the example that Sasha mentioned. How we compute for each word, we can compute certain vector. So basically here I took some word embeddings using this like very popular glove algorithm and just plotted distribution of distances from a certain query point. And as you see, it has a pretty nice shape. So there is a bulk of points that are sufficiently far, but nearest neighbor is much closer than like most of the points. And precisely because we have this gap between nearest neighbor and most of the other distances, like similar algorithms, similar space partitioning based algorithms allow you to recover exact nearest neighbor.
But the approximate nearest neighbor is just the same as exact nearest neighbor.
No, not necessarily, right? Because there are still other points that can be just like a little bit further than nearest neighbor. But the point is there are few of them, and we can just filter through all of them, pretty much. Like, yeah. So here's a slide, like obligatory slide about Werner diagrams. Again, I've already mentioned it. Let me just briefly repeat that in R2, that's exactly a way to go, because in 2 dimensions, Werner diagram has linear complexity because it's a planar graph, and you can show that it has linear number of vertices as well, and as a result, linear number of edges. So, and there are some smart ways to pre-process it to perform point location. But in D dimensions, that doesn't work because space complexity would be something like n to constant multiple times d. And that's not good. And the whole philosophy here, if I may use this word, is to use, instead of Werner diagram, use like cheap, crude replacements of it. So that's exactly what we've seen in the hypercube case. So we kind of like build some space partition. Of course, it has nothing to do with Werner diagram of the points. In particular, like it doesn't, like when we built this partition, we didn't even, so distribution of these partitions doesn't depend on the points at all. But at some level, it kind of resembles Werner diagram in the sense that if you look at the query, then like typically nearest neighbor would be in the same part, and like close points would not be in the same part. And that's exactly what the motivation for all these space partitions is. So we would like something algorithmically simple, not as like complicated to handle as like true Werner diagram, but at the same time that should respect small and large distances. Again, I'm not being precise here, and that's for a good reason, because actually, like if you try to formalize the definition of something like this, there are many possible definitions, and actually, like for different applications, you need a different definition. And for this talk, I'm not even going to bother with giving a precise definition here, because at the end of the day, what we will obtain, it's some like heuristic object, as we will see later. But if you'd like to have some definition in mind, you can think what we've done for the Hamming space. So for the Hamming space, we just said that I'm generating a partition that close points with decent probability, with at least some probability, end up in the same part, but far points end up in the same part very rarely. And that's exactly one possible definition. This is called locality-sensitive hashing. But again, not too important. So as Sasha asked me a very good question, would I be able to construct several partitions in this talk? And the answer is no, I will not be. Actually, like, I'm not sure if it's for a good reason or there are some obstacles to that, but the point is there are some actual motivations where just constructing one partition is enough. And one such motivation is when you want to run a nearest neighbor search on a distributed cluster, on a cluster of computers, on a distributed system of some kind, or something like this. So what's the setup here? So the setup here is we would like to distribute our points across n machines, right? Suppose that we have, I don't know, trillion data points or something like this. So then it's okay. So one thing you can always do, you can just do a random partition, but random partition is not that great because it's much more natural try to respect some locality. So basically, maybe a given machine should contain a points that are kind of like situated near each other. Why this is better? Because then when we have a query, we can hope to assign it to just a few machines and not to like all of them. And for each machine that we assign the query to, we use some kind of like local nearest neighbor search algorithm per machine. It can be linear scan, or it can be something that I've described. It doesn't matter. So the point is, like, we would like to partition points into machines such that when we get a query, we can very quickly say, okay, I partitioned into 20 machines, but actually, if you just look at this and this machine, like 3 out of 20, then with high probability, you will recover nearest neighbors. With high probability over like some query distribution or something like this. Is this motivation clear? Sasha, can you ask me something? Because like you disappeared and...
No, I think this is more or less clear. I think it's better now to say what is the algorithm and then return to how it's used.
Sure, great.
Excuse me, just a question. There was some comment by Grigory Kebatiansky. Just if I can see it, maybe.
Oh yes, okay. Yes, but okay. So here is the thing. Linear. Okay, that's a very good comment. So let me first of all repeat it and then explain like what's going on. So so Grigory is saying that it is NP hard to find nearest vector to a linear code, even up to a constant factor with a distance. Okay, first of all, what is this problem? Oh, I think my screen sharing died, but okay, I'll recover it in a second. So basically, linear code is just some.
Sorry, I think that's my fault. I played with the system and made Andrei Ramashchenko the presenter. I'm sorry. I should make you the presenter back.
Okay.
How do I do it?
Comment on linear code. So we know what is linear code, I guess.
Right. So the thing is, basically what this result says is that it's NP hard to find nearest vector. Okay. But the point is, linear code has exponentially many vectors, right? So in my notation, n would be 2 to dimension of the code if your code is over f2. So even if you use nearest neighbor algorithm, so it will give you only like polynomial saving in this size. So of course, even if you apply nearest neighbor algorithm to this closest vector in the linear code problem, then you will only obtain like improved constant factor in the exponent. So what I'm saying doesn't contradict this NP hardness results at all. But in fact, for linear codes, it's a much more structured problem than unstructured nearest neighbors, like I'm talking about here. So in fact, there are better algorithms for this problem, though they're still exponential time. So it doesn't contradict what I'm saying doesn't contradict this NP hardness results. But these algorithms like this can be used to improve exponent in the exponential time algorithms. So it is very related, but it's in some sense it is a slightly different realm. It's like more structured, but you can use still these algorithms, though this is not the best you can do. Okay, so let me return to let me explain the algorithm as Sasha suggests. Okay, let me share my screen again. Yeah, okay, so before I tell the algorithm, I'm about to do it, but let me just restate the problem formally, slightly more formally. One last time. Again, I already like go around it, walk around it like over and over again, but like, okay, so this is almost it. So we are more or less like at the algorithm description. So basically we have n points in RD, and I would like a partition into m parts such that each part contains approximately n over m data points. So I want my parts to be balanced. And for a typical query point, most of its k nearest neighbors are in the same part. And moreover, I want my partition to be algorithmically simple. So this is the problem I'm solving. And here, a great question might be, what is a typical query point? So I'm kind of assuming that there is a implicit distribution over query points that I don't know, but I kind of like maybe receive samples of the queries, or I can do something about it. So that's exactly...
Sorry, if you say are in the same part, they are in the same part with the query point, or just in the same part?
Yeah, with the query point. Yeah, with the query point. So basically, if I locate my query point, I can just search through this part and obtain k nearest neighbors. So, okay, so like this is, it's not very well-defined question, but in principle, it's like somewhat like reasonably defined, right? And it has nothing to do with learning. It's purely some kind of like geometric partitioning statement or optimization problem or something like this. But as you will hopefully see, learning arises somewhat inevitably. But before learning, let's solve a simple case of this problem. So simple case is, suppose that query is not just like some arbitrary point, or it's not even like point coming from some unknown distribution, but like suppose that query is generated in a very specific way. Let's just say that our query is a random data point itself. So basically, I have n points, and then I say, okay, let me pick a uniform sample from these n points, just like ith point, and declare it to be a query. So of course, if it is a query, then the nearest neighbor is the data point itself. So this is kind of stupid. But because we look for k nearest neighbors, this becomes an interesting question again, right? Mm-hmm. But okay, so if you think for a second then about our problem, what we want in that case, so it's pretty easy to see that it directly corresponds to balanced graph partitioning. So what we need to do in this simple case, we just need to connect each point to k nearest neighbors, right? Build a so-called KNN graph. And then we just need a balanced partitioning of it, because probability of error is exactly how many edges our partition cuts, right?
Mm-hmm. So balanced partition is what?
Okay, balanced partition. Okay, I should have mentioned it. So it's so we would like to partition our set of vertices into m parts of approximately equal size.
Yeah.
Maybe we can say that each part has size at most like 1 plus epsilon times n over m. Such that number of edges that connect different parts is as small as possible. Mm-hmm. So this is exactly what we want here, right? Because if we generate query to be a random, uniformly random data point. And basically, you can use your favorite algorithm for this problem. Again, you can use spectral partitioning, you can use heuristics. We use certain like combinatorial heuristics that not developed by us. Like basically, there is a whole group of people in Germany that essentially just do this graph partitioning for living, because it is a very important problem actually in many other application domains. But the point is like this gives you a good partition. But why we are not done? Why we still need learning? Why this is not the end of the story? So this is not the end of the story for two reasons. First of all, we restrict our queries to be data points. So of course, in reality, our queries can be any point, and like even though we have a partition of a graph, it doesn't give us a partition of RD. So we just need to do something about it. So we need to generalize our partition from this like nice graph to the whole space. But another point is that this partition is not necessarily algorithmically simple. So this is just partition of a graph into several sets, and it like potentially it might induce some like potentially a priori it might correspond to some crazy subsets of RD. So we need to in some sense like normalize it in some way so that it's like it can be algorithmically useful. And so that's where we use learning. Okay, so first of all, let me maybe say a few words what do I mean by learning here. So I mean by learning here supervised classification. So what is supervised classification? It's basically when you have a bunch of inputs. So usually we think of inputs as points in RD. So these are like feature vectors. Sometimes these feature vectors are handcrafted. Sometimes they're obtained using some automatic procedures. But it's not too important for this talk. And then we have such input, feature vector, and then we have output. So for example, like one good example here might be we have a bunch of pictures. And for each picture, we know what's on it. It's like cat, dog, airplane, house, and whatnot. And basically, after seeing many such examples, we would like to construct a classifier. So classifier just means, effectively speaking, partitioning of the whole feature space. So the whole space where these feature vectors lie. So in the example of pictures, that just means for each picture, we should be able to output what's drawn on it. And there are so basically, yeah.
It's quite clear that you need to classifying any points, not only the points which were given, and this exactly is the
exactly. So that's exactly what I mean by like learning arises inevitably, right? So I hope you agree with this here. So basically, it's exactly the supervised classification problem where we have basically we already have a bunch of labeled examples, and by labeled examples I mean like a result of our graph partitioning, and then we just want to train certain classifier, aka space partition, that predicts for a point, it predicts which part it should fall in.
Okay, so now two questions. First, are you allowed to change partition? You find optimal partition maybe, but are you allowed to change the partition of graph a bit to make the classification?
Yes, absolutely. So that just corresponds to not getting perfect training error. So basically, yes. So on this picture, I drew a simple example where this is not happening. So here we find a perfect separator, linear separator between two parts. Of course, in reality, this is not happening. So we will screw up on some points in the graph, but hopefully just by like on a few of them, and that will be okay.
And what kind of so if you have two classes, this could be a linear separation, and if you have many classes, is just what a kind of polyhedron.
Well, okay, so there are like several things you can do. So what we do for several classes, we just like we live in 21st century, so let's just use neural networks for this case. So it will not be a polyhedral partition, it will be partitioned into some. Actually, like for neural networks, it depends what your architecture is, but for architecture that we use, it will still be polyhedral partition. Just containing from like very, very many faces. Mm-hmm. So, but again, that's not the it's an interesting point, but it's not the main point. So the main point here is that you can essentially use black box any supervised classification technique that works well will work well for this problem. So that's exactly the nice thing about it. So let me say a few details. So as I said, for graph partitioning, we use certain combinatorial local search-based heuristics. Again, I'm not going to say what this is. It's, again, like a very well-established line of work. So we use specifically the algorithm by Sanders and Schultz. But for learning, we use, it depends what we want to obtain. So, okay, so here is what the trade-off here is. So it's not just enough to do this learning. Later, we will want to classify our queries quickly, right? So it's very important that the model is actually simple. So that's why, even though linear models, they're not as great as neural networks, we still benefit from learning a linear model. So for example, when we want to partition into 2 parts, we might still want to resort to a linear model because later it becomes like very easy to classify. It's just like ends up being a single dot product between query and whatever your hyperplane is. So if you want...
So it seems that now we completely switch to some experimental things.
Yeah. I never promised you any provable guarantees.
No. Just... No, it would be nice that if machine learning can prove something, it would be a great achievement, but you don't claim this. Yeah, okay.
Sure. And another thing I should say is that reality is a little bit more complicated than I've said for the following reason. So I gave you a motivational example of this like distributed search where we like partition points into like 20 parts. And then when query comes, we say that we should send query to this, and this machine. So far I've been only talking about like predicting one part. So in fact, we need to predict, we need to predict a ranking of parts rather than a single part. But more or less this can be done. So this is like a technicality. It's like important technicality, but conceptually it doesn't matter that much. Okay, so there are some experiments I can show, but maybe I should also say what we compare our algorithm with. In some sense, it's not that much about like we are better than these algorithms. It's also like what are the alternative approaches, right? Because I kind of like showed you one way of doing it, but what are the classic ways that people were using before? So, for example, again, in this like in theoretical literature and in practice, there are these things like I've described, like locality-sensitive hashing for Hamming distance. Like there is also this idea, it's like very simple. I can also explain it like very quickly. Use k-means clustering. So what is a k-means clustering? This is just a way to say that you have n points and you want to partition them into k groups to minimize like what's called quantization error. But what this actually is that we would like to minimize average squared distance within a cluster, roughly speaking this.
Mm-hmm.
And this is a known, very well understood problem. It's actually NP-hard. It's even NP-hard to approximate. There are like approximation algorithms for this problem, but there are also some very simple and very simple heuristics that work well. It's called like, for example, there is one very popular heuristic. It's called Lloyd's algorithm. The idea is very simple. You just say that, okay, initially I partition points into clusters at random. Then within each cluster, I find a center. So basically just arithmetic mean. And then I reassign points to the closest mean. And then I keep doing it. And then it kind of, in a good case, it would converge to some nice solution this way.
Mm-hmm.
And for this problem that I've described, finding nearest neighbor friendly partitions, k-means was a standard established baseline, and it actually works great. And it's very simple to use. But one difference between these approaches is that k-means optimizes the objective function that is the wrong thing to optimize here. So like if we want to not cut out nearest neighbors, why the hell a priori we care about minimizing square pairwise distance, right? It kind of feels like, these things have to do with each other, but maybe not as much. So in some sense, our work obtains certain improvement over k-means. Essentially, I would argue because of optimizing the right function. And basically, I told you that sometimes it might make sense to partition into 2 parts. Usually, you use these bipartitions recursively. So you build the decision tree of these bipartitions. Mm-hmm. And what people used before for those was something called Pca Tree. So Pca Tree is a spectral approach to finding these recursive bipartitions. So it's basically when we compute take our data set, interpret it as a matrix, and compute top singular vector. And singular vector gives you, in some sense, like direction in which your data set is the most pronounced, and then you just cut it in the middle. Mm-hmm. And then you do it recursively. So this is called Pca Tree. And again, there are some experiments. Maybe let me not waste too much time on it. So yeah, we're better, sure, blah, blah, blah. So that's pretty much it. That's all I can.
Yeah, but just about the experiments. So definitely you have some kind of data set but
Sure.
can you say from which to which kind of application this data set
Right.
is tuned?
Right. So we tried. Okay. So in the paper we have more experiments, but here I'm showing. So two main experiments are for word embeddings. So that's exactly the thing we discussed. So it's basically just like for a word, find 10 most similar ones. So it might be a little bit silly problem in itself, but let me just say that this idea of like producing embeddings, it can be done not only for words, it can be done also for the whole like paragraphs of text or sentences or documents. And basically then this idea of like retrieving similar word embeddings becomes like very meaningful application problem in itself, right? So you want to like, given a text document, find several similar ones. That's exactly what Google does and all the search engines do. So another application we tried was image retrieval. So there is this standard dataset SIFT. It's a little bit old at this point. No one is using this image descriptors anymore. So people are using feature vectors originating from neural networks. But it's a standard benchmark. That's why we used it.
So in some sense, to the first one. So you have this million of hundred of vectors of length 100, and so you divide them in how many classes just to get some idea.
Right. So we run several experiments. The smallest number of the smallest number of parts
Just
we divide is
typical case, just to get some feeling what you are doing.
Okay, 256.
256 classes.
Yes. So, and if you divide into 256 classes, then you can just say, okay, query comes, and then maybe you need to look only at like 5 of them, something like this. I don't remember the exact number here, but something of this sort. And just restricting your attention to just 5 out of 256, you can essentially almost not lose in like nearest neighbor accuracy.
Okay, yeah.
Yeah. So that's the whole idea, and we kind of observed that our results are fairly consistent between data sets of different nature. So to me, it kind of suggests that maybe it's like far-reaching generalization, but to me, it suggests that if you are in this situation, if you have this like gap between nearest neighbor and typical distance, then maybe our heuristic would work well, kind of. So
how sensitive is to the algorithm used in the first part and in the learning part?
Of course it is sensitive. So for example, it really requires you to like, okay, so we tried many things. So there is some work on like I'm not gonna name people here, but there is some recent work that claims to produce like very fast graph partitions at scale, whatever it means. We tried to use those, but basically, like, it's very important to obtain good graph partition. Basically, yeah, it's actually like weirdly enough. It's not really weird, but it ended up being the case for us that finding a good graph partition is computational bottleneck here. So learning is actually fairly easy if you already have a graph partition. Finding good graph partition, that's where it takes like maybe hours.
But good means that somehow well adapted to what you do later. Or
no.
Just
actually, no. And that's, you're asking a great question. So by good here, I just mean small number of edges between parts. But of course, the next possible step would be to do these things together, right? So it's natural to try to optimize graph partition and space partition jointly in some way, so to make them aware of each other. So that we don't know how to do well. I have some ideas, but I've never tried them, and I suspect that this should give pretty big gains. So in some sense, what you are saying is a very good suggestion for the next step. So basically try to find a graph partition such that later it will be like the most neural networkable and vice versa in some sense. So how to do it, it's an interesting question. But definitely I think it will give certain, like, I have some indirect evidence to suggest that it will give big improvement. Okay,
and
yeah.
So you have some kind of open source software which does something, or library or whatever.
Yeah, we released our code. We released our code, so it's on GitHub. You can check it out. I can.
Okay.
Yeah, but the point is, someone tried to use it and they did not quite succeed. So don't expect much. But it's there, so at least.
No, you mean they didn't succeed to understand what are the correct README to compile it, or the
I think they failed to build some dependency that we rely on, something like this. So it's not exactly our fault, but it's
yeah,
like.
But you always fail to do this, yeah.
Yeah. It's like basically that's the problem with research code. So I take full responsibility for this, but at the same time, so just in case, I'm sending the link to our implementation.
Yeah, and if imagine that one can build it, what will kind of be a toy problem when it can be used to deal with?
I mean, anything, any kind of like feature vectors. If you give me like n vectors in sufficiently high dimensional space, it should hopefully produce something reasonable, unless it's some pathological or degenerate case. In fact, following up on our original discussion about edit distance, I have a hunch that these techniques can be useful for non-Euclidean case as well. Because, for example, graph partitioning step, it doesn't care what your metric is. It can work for any metric. You just connect each point to k closest ones, and then you just partition the graph. But of course, the learning step here implicitly uses the Euclidean structure, because it uses, for example, when we train linear model, we just use that original, we use the original coordinates. Mm-hmm. For the edit distance, it seems like the wrong thing to do. So maybe we need to do some feature generation or some transformation. I don't know. I need to think about it. That's another interesting direction, to try to generalize this approach to non-Euclidean case, and that would be wonderful, because like then we can just like, okay, we don't need to try to read that scary paper anymore that produces best embeddings into L1. So
okay,
yeah,
so now I think it's a good time to stop and ask whether there is some questions, or I try to ask something, but probably somebody else can also do this.
Yeah, in theory, the microphone should work, but if not, you can try to write it in the public chat, and Ilya will read it.
Yeah, you are again using a bad microphone. I am saying always use the same thing, but it's true. Okay, so that also my idea was to have some more general kind of interview or discussion about, because here I don't know, maybe some people came from other communities, but there are a lot of theoreticians who heard a lot about machine learning, but have no serious idea what is possible and what is impossible, what are the main achievements, and what can you expect from all this.
I'm still not fully sure why I'm in position to say anything meaningful on this, but like, okay, so be it. Like, if
yeah, okay. So no, just if you want, kind of imagine you want to tell people what are the main achievements or main classes of machine learning, and what you should learn if you want to become acquainted a bit with the theory.
So okay, so here is my one sentence summary of where we are in the machine learning. It can be totally wrong, by the way, because like this frontier, it like changes every week, and that's one of the, in my mind, like one of the most dissatisfactory and disappointing parts of this community is that it's too big, and it's almost impossible to keep up with even like the main things that are happening there. I mean, on one hand, it's exciting because it's it's always nice to be in like exciting and fast-pacing field, but at the same time, there is I would argue that there is very little space for like so you can't afford to think about a problem for a year because someone else will solve it if it's solvable. So it's a little bit depressing, and like many people express these sentiments. But if my understanding correct, then I would say that we made huge progress in like supervised classification. So basically, if you have some kind of like inputs with labels, and then you want to prepare for like further inputs and be able to produce other labels, then this problem, I wouldn't say it's like mostly solved, but at least there is a huge progress have been made, and that was the focus of the past, I don't know, like couple of decades or something like this. But right now people look more and more into like not exactly supervised learning. So like, for example, imagine that we have still bunch of pictures, but we don't know anymore what is drawn on each picture. It's unreasonable to expect us to have labels for, say, all the images in the internet, right? Because that would require some humongous labor to just like label all the pictures we can find. So people try to look into like semi-supervised learning or like unsupervised learning, where we have labels, for example, only on some of the pictures, but can we still utilize the fact that we have lots of additional pictures, and still like can this give us any additional leverage? And the answer is yes, if you are like careful enough with this. And so my understanding is that people move towards like unsupervised tasks and unsupervised learning, and in some sense that's where we are now, kind of. That's like, again, don't quote me on this. This can be completely wrong. Maybe someone else comes and says, this is already solved. Now this is the like next goal. Okay, fine.
No, but for example, I don't know. Imagine there is a standard things. For example, there is a kind of voice recognition.
Sure.
And where is the boundary here? For example,
that's a great question.
If we have when several people talk like we are now talking in together or in a room or whatever, is there a chance to transcribe it? Or
I don't know. I mean, like, all I know is that I know as much as clearly any of you, namely that if you buy any of this like smart whatever, like Alexa or any of these devices, they can recognize your voice even without any pre-training. So they just like, actually that's a thing that impresses me, again, not as a researcher but just as a layperson, that it doesn't even tune to your accent. It just like immediately recognizes what you're saying. So that
I would say the different. When my French relatives speak to this Alexa or to this smartphone, even I can understand what are they saying. But if they say something normally, this is not possible, both for Alexa and for me. When you speak to the device, you speak in a special way.
Maybe I can't speak like real English. I can only speak dumb English that Alexa can understand, no problem. So that could very well be the case.
Just try Russian and you will probably see them.
Sure. So, I mean, okay, in any case, I know nothing about speech recognition. It's only as a like consumer of these things. So
okay, and another question. Imagine, I don't know, we have a mixture of two photos. Like in old times, when you don't change the film correctly, you get an average of two pictures.
Sure.
Is there any chance to separate them to each of them, or it's far beyond them?
So I haven't seen any results like this. But if I to guess, I would say that yes, it should be possible.
Mm-hmm. And for example,
moreover, I think that it shouldn't be even that hard. Like, okay, so what I would try to do, let me think. What I would try to do is to precisely try to do this separation in the feature space. So, yeah, okay, no. I again, I don't want to speculate, but again, my guess, just again, wild guess, that it should be possible. Yes. Moreover, I think that there might be papers about this.
But for example, why then, if things are so advanced, why, for example, this capture things still exist? It seems that they ask us to recognize something which is not very difficult.
So that's a great question. So I think the big problem of machine learning, that's another like big milestone and challenge in some sense. So, for example, in this result that I've described to you guys, we kind of implicitly assumed that distribution of queries and distribution of data points is not that different from each other, because otherwise these partitions will go berserk. And that's again, like all the theoretical results about machine learning and even like practical results, they kind of assume that like queries come from distribution that is similar to distribution where your data points come from. And right now there has been a lot of activity trying to handle this like distribution shift. So basically you can very easily fool any machine learning model by just like, you know, presenting it some example which doesn't look like anything it has seen before. And moreover, there is this like subfield of this called like adversarial examples. I'm sure you've seen all these pictures, right? Where you take a picture of a cat, then you perturb each pixel just by epsilon so that you don't see any noticeable difference, yet neural network will classify it as a dog with high confidence. So basically handling this like adversarial inputs and handling this like inputs from other distribution, this is something that people struggle a lot, and there is partial progress, but it's very far from being done. So that's why CAPTCHA is just like probably they just change distribution from time to time and you just have no time to retrain or something. At least that's what I would do to avoid some machine learning attacks.
So I don't think that we should consider CAPTCHA is something that is not doable. I think that you can solve any particular CAPTCHA, but they change styles, and so the cost you have to invest to solve every specific CAPTCHA probably is too high to you know.
Yeah. So it's much easier to just like you know there are services where like bunch of people would solve CAPTCHAs for you. You can just if you want to break CAPTCHA, no need to train any machine learning model. You can just pay like $100 and then like 10,000 CAPTCHAs will be solved for you by people.
Yeah, but then you can use these results and use learning based on this, and then save your next $100.
Yeah, but you waste more on GPUs. To rent GPUs, it would cost more. So that's the problem to like train neural network. That's by the way. Okay, so here is another challenge in general. All this. Okay, so our paper in that regard is like nothing. So we just needed. I think we trained our models on like 4 GPUs, and it took us like each training takes like several hours. Not even several hours. It's probably 1 hour. So it's like nothing. But the problem is if you want to solve some serious problem that serious people solve these days, like for example, like learn image classifier or like do some speech recognition or do some kind of like, I don't know, like some natural language processing task, then it requires lots of hardware and like for a long time. So it's just like extremely expensive. So for example, if you are like professor in university, then you barely can afford to have like hardware in your lab to even like recreate results from other papers, let alone do new research. So that's a big problem actually. So that makes research in this domain very like non-democratic, I would say. So in that sense, like big companies are doing much better, but even big companies, like for example, there has been recent, well, it's by machine learning standards, it's not so recent. It's probably already like 1 year old. So that's like ancient history. So there has been this result called BERT. So it's some kind of like word embeddings on steroids. Again, let's not discuss what it is, but it's a huge advancement in this like natural language processing tasks. So the point is, until recently, only Google was capable to run this experiment. Just no one else, like Facebook, Amazon, Microsoft, no one else had the hardware to even just repeat the experiments, let alone like universities. So now I think all these companies can do it. So they caught up by spending like some obscene amount of money.
So they don't improve the algorithm, they just buy a lot more of new hardware.
So on one hand, yes, and that's actually one criticism from like theoreticians, as I would call them. So, they don't do anything smart, they just do gradient descent on thousands and thousands and tens of thousands of like some specialized hardware devices or GPUs or whatever. But in my mind, that's actually pretty exciting in itself, that like by putting more computational resources, you can actually improve results. Like a priori, that shouldn't be like that. That is not obvious if it should be the case, but it is. And I think that's interesting to see the limits of all of it. So that is kind of exciting. So basically, in some sense, it just like puts us out of profession because like no one needs like fancy algorithms there. It's just a question about, you know, like running gradient descent more efficiently. Of course, this is oversimplification. This is not quite true. There is still a place for like fancy algorithms somewhat, but at least at the basic level of it, this is just like, you know, let's run simple thing just like at as big scale as possible. So.
And then returning to profession. So, for example, there is a lot of success related to what is called this neural network or deep learning or what. I don't really understand all these words, but I understand that there is some kind of several layers of simple elements which are tunable, and there is some way to tune them to get in the
gradient descent, just using gradient descent, basically, nothing more than that. So you just basically like say that, okay, my final function will be composition of basically like matrix products and some non-linearities applied like component-wise, and you do it several times, and then you just run gradient descent on this. That's it.
Mm-hmm. And for example, but what is the state of affair? For example, imagine we know that there is a kind of a circuit which efficiently does something. So we know that there is efficient circuit for sorting or for sorting network or whatever.
Sure.
Is it can we now find it? Before we knew that it can be constructed in a very delicate way using something. And is there a chance now to find it automatically for a reasonable size of inputs?
So
without
yes, what you are talking is a whole research direction. So it's kind of like so there are like several aspects to it. One is what you say, right? So there is this fancy algorithm that it took us decades to invent. Can we reinvent it or maybe even improve upon it using like neural networks? And yes, people do it. And in some cases, the answer is yes. In some cases, the answer is no. So first of all, by the way, one unsolved problem is to learn teach neural networks to multiply two numbers. So this is not known. So there are some like very simple tasks where like gradient descent based approaches do not work.
And compute majority.
That I don't know. So there are papers that study this. I just don't know this literature at all. But at the same time, for certain data structure questions, even like this paper that I presented to you, it can be seen as like one manifestation of this. It's kind of like we take a classic algorithm and supercharge it with some learning component. And that is a pretty active area. And in some cases, we can actually like reinvent existing things. Like, for example, there is a whole industry of like rounding linear programs. So it's some kind of like to run approximation algorithm, we solve some LP relaxation, and then we round it using some like fancy combination of rules. So many of these fancy combination of rules were invented like using machine learning. So there are some papers on this.
But you mean like, that machine learning is used to make rounding for any specific case, or just to invent some formula for
I think both. So both of these things can be done at least in some cases. Not just for specific case, but it comes up with rules in some sense. So
and are there some, I don't know, some theorems or which probably I don't hope that they will explain the success of some practical things, but maybe what are the theorems which you need to know as a kind of getting a background to understand better this practical algorithm, even if they don't guarantee anything?
I think approaching this field through like theorems, it's not the best way to go. I mean, there is some theory of this neural networks and deep learning, but it doesn't seem to me like this is the. I mean, like I know how we all feel about it, right? It's like, you know, like our first instinct: what can we prove? What can we show? But I think in this case. So here is my opinion. It's completely controversial and probably like I will be crucified for saying something like this. But in my mind, the value of like theory for this thing is like not very high unless you axiomatize your data. So basically, if you can say that, so you can't prove anything about neural networks without assuming some distributional assumptions on the data. But in my mind, no such assumptions can be adequate. Like how can we even talk about like distribution of natural images? What the hell is this? So we can't if we cannot specify what is distribution of natural images, what properties it has. And I argue that it's very hard because it's a very high dimensional distribution and we see only very few samples of it. So in some sense, we are trying to like sense the unsensible. So unless you like give me some postulates or axioms about data distribution, then all the subsequent theory, it's like really on a clay feet. I am not buying into it in some sense.
But for example, imagine you want to, I don't know, there are this chess program which play very well against human opponents and even against other chess program.
Sure.
But imagine on the other hand, we have some classification of end games with limited number of pieces using just dynamic programming.
Sure.
So, for example, is it possible to use this? For example, is it possible to train, I don't know, on 5 pieces end game and to get something reasonable for 8 pieces as end game?
So you are saying that can like okay, so like reformulating what you are saying, can this like empirical learning benefit from provable learning in some sense?
No, okay. What I'm saying that there are cases when there is no problem of input distribution. We have all 5 pieces end games classified, and so you can do whatever you want, but you with them. But you want to construct a correct classification and faster correct classification for I don't know 8 pieces.
Like okay, so
not just
I think your analogy, analogy, your like similarity can be like instantiated in several possible ways. So one possible way is like, can we develop some primitive theory that would still be useful to like for understanding or for helping?
Just learning the theory should be useful for future practical work.
I mean, like, okay, so there are all these classic results. Like, I've seen that you guys even had a discussion about like PAC learning and VC dimension, right? For example, even this like classic theories, they're still somewhat useful for understanding things about neural networks. Like, again, like I know nothing about it, so I know about theory of learning even less than about practice. So that's because, as I said, I have certain doubts about like meaningfulness of this activity. Again, like
so for example, there is something which I heard many times, first from Volodya Vovk and then from other people, which is called support vector machines. And whether it's useful or not.
Exactly. So I wanted to say this as well. Support vector machines is probably the last machine learning model. It's just linear classifiers. Okay, support vector machines is linear classifiers, more or less, like
and
with some caveats.
Theorem.
Yeah, there is some theorem. It actually is like these theorems are simple corollaries from like VC dimension bounds. So we just use the fact that like VC dimension of like hyperplanes in RD is like D+1. So like poly D samples like coming from input distributions are enough to like find the best linear separator. That there is no more to it than that. Like again, I'm sure there is more, but at the conceptual level of like my limited understanding of it, that's the end of the story. So whether it is useful for neural networks, I think so, because like from what I understand, like some VC bounds on some like sets induced by neural networks, they're not like completely vacuous, and maybe they even tell us something. But again, like I don't know enough to actually like make any assessment. I just know that people studied it, and these are like well-known papers. So I guess like at least my a priori assumption would be that they're not completely bogus. So there is something to learn there. So yes, there are some connections. There are some connections between this classic theory and some like more recent developments.
But still,
in chat, probably it's out of date, and we have switched to another topic. But if you can see
it. Hello, Andrei.
Yes. Why Sasha is asking question? There were some question posed on on that.
Oh yeah,
public.
Sorry. Yeah, I should.
Oh, but we can say that. Oh, okay. Well, I mean, we might all have very different standards for theoretical justification. To
What
me,
is
this
CNN?
doesn't. Convolutional
Sorry,
neural
answer
networks. Okay, so what is
Okay,
convolutional
what is
neural
convolutional-
networks?
Yeah.
So it's basically, okay, so I told you that roughly speaking, neural network, it's composition of like linear transformations and some non-linearities. So sometimes imposing full linear transformation might be a bit too much because it might mean like too many parameters. So even in early works in like image recognition, they observed that we don't need like full linear transformation, like basically full matrix. It can be of very particular structured kind. And one structure you can impose is to require your linear transformation to be convolution. So convolution here is a little bit of a misnomer. It's not what we usually call convolution. It's related, but not it's not exactly the same. So it's basically like how to explain it? Like if you have an image, for example, then you kind of like put a small window like 3x3 or 5x5, and you put it in every possible position and compute like respective dot products, and weights in your window are always the same. And this gives you some linear map. And again, this is like slight oversimplification. In reality, convolutions, there is a little bit more to it. There are like several channels and whatnot. But roughly speaking, this is like some informed way to impose some structure on your linear transformation that you expect to work well in your domain. And for images, like imposing this like convolutions makes sense precisely because they supposedly are translation invariant. But for example, like what does it even mean? To what extent this is theoretical justification? Like whether you can impose any other structure on your linear transformation that would give similar results. I don't know if people tried actually. Maybe they just like, convolutions work well enough. Maybe we should just not bother with it. So it's not clear to me to what extent this is justification of anything, but definitely it definitely is a certain way to build neural networks that is inspired by certain common sense, and it works well. So yes.
So just can you confirm my impression of what you said, that if you want to, I don't know, to teach the university student so they can work in a company which does some machine learning for some practical purposes or something like this, then of course they should study what is a gradient, what is the function of several variables, what is a derivative, and so on. And probably they also should study what is a large matrix, what do you do with eigenvector, and what is the quadratic form or something like this.
Sure. So that's exactly the thing I like about machine learning the most, because it requires people to learn a little bit of analysis, linear algebra, probability. So that's a nice thing about it. Yeah.
And also they probably need to learn how to program these GPU things. What is the?
You don't need to program them. That's another nice thing about it, is that there are these frameworks these days like PyTorch or TensorFlow or like whatever other thing will be invented tomorrow. They basically outsource these matrix operations to GPUs for you, and you just it happens seamlessly. So of course, yes, if you want to like construct such frameworks, then you need to know the like nitty-gritty low-level details. But most of the machine learning researchers or practitioners, they just like use this as a black box, and it is perfectly adequate. And it is quite impressive that they were able to abstract it out so well. But you don't need to know what CUDA is. You don't need to know what. You need to barely know like that GPU, there is this thing as GPU and it has such and such amount of memory. So if you can like fit all your like tensors into your GPU, then you won.
But in which, so do you believe that these frameworks are somehow universal in the sense that everything which can be done fast on the current GPU
so
can be done through
this framework, like kind of. So I can tell you what these frameworks do in disguise, nothing much. So what they do is they just do essentially matrix and what they call tensors. I don't like this terminology tensors because it's like multidimensional matrices, let's call them that. So they do all this like convolutions, matrix multiplications, everything else like efficiently on GPU. And then they also allow you to just specify certain computation graph and automatically differentiate it, right? So basically to do this like gradient descent, roughly speaking. So basically if tomorrow you discover some other nice operation that you can implement on GPU, and we will figure out that it might be useful for learning, we will just add this operation to this framework and it will pick it up. And like basically if we will also explain it how to differentiate this operation, then that's it. So basically these frameworks are like, they are not probably currently universal, but they're extensible in that sense. So, but again, that requires slightly deeper dig. So it's not just enough to, be usable.
Definitely, GPU have some features which are used for, I don't know, for making textures or for making moving things, or which are probably not used in this.
Yes, but effectively GPUs are used as a way to like do Fourier transform and matrix multiplication. So yeah, for these two things.
And for example, you don't need to teach these people complicated algorithms or data structures or God forbid NP completeness or P-space.
No, I don't think so. I think for machine learning, like in some sense, like mathematics is more useful than like computer science in some weird way, if it makes sense. Yeah.
And and I don't know, for example, imagine you want to construct some system, I don't know, for operating trains or I don't know, in the underground. So the standard approach was to develop some language, some model, some I don't know, differential equations, some proof of the no collision happens, and a lot of different tools and languages and so on. And is it now all obsolete and you need to just to collect a lot of data and
No, it's not. So okay, let me try to interpret your question. So your question is like how useful learning techniques are for like planning and for like this kind of tasks.
Car driving.
So
or
I worked. Okay, so first of all, there is this like quest of self-driving cars where like people use a lot of learning. So in that sense, it is true. But on the other hand, if you take like other angle at your question, so I interacted a lot within Microsoft. There is a group of people who do like operations research. So pretty much they like optimize like how to assign goods to trucks or like how to, send people who do catering to venues in an optimal way so that, like people are happy, clients are happy, everyone is happy. So they're not using learning that much because the problem with these problems is that they're highly discrete, and there doesn't seem to be like useful parameterization where like gradient descent works well. So they use different approaches. That said, I'm sure there are some scenarios where learning might be useful, but it's not a mainstream thing in these kind of scenarios. But for example, when you are in like self-driving car and you like get some picture input and whatever this like LiDAR, then of course learning techniques are great because that's what you need to do. You need to do like image recognition and some kind of control theory. So in this domains, learning is like the main thing.
So okay, for just a very specific question, you know that if you have a kind of a long stick, then you can balance it on your hand, moving hand in different directions.
Sure.
And then imagine you want to construct such a toy which will do it automatically.
I think such problems people try to solve. So this is some area I know almost nothing about. It's called reinforcement learning. So it's basically like interacting with environment and like making environment do what you want. So it's kind of like what you are saying. This is a good example of that. Like robotics needs loads of that, and like there are some other areas. Again, like I know literally nothing. I don't know even the basic definitions of this area. This is something I never learned. But they do claim that they can solve problems like this. Yes.
Yeah, but before people, for example, studied, I didn't know this differential equation, try to prove stability, to find the eigenvectors and their complex argument and module, and to be in some space, half space. And there was some theory, complicated theory of control. is it now that you can just watch how people do this and get some kind of replacement?
So I doubt it. I think these techniques should work together. There has been recent hype about like robotic hand assembling Rubik's Cube. So I don't know what took them to do this. It is somewhat impressive. So I assume that it should be fusion of like learning approach and some classic control theory. Yeah.
Yeah, just a short comment about robots. We have a huge robotics department in our lab here in Montpellier, and I've attended a few talks. I cannot say that I understand it, but I have heard both kinds of explanations. There was this old-styled explanations about the differential equations and some mechanical tricks and some old-school math. And there were talks where people thought that we just do some machine learning, and of course we cannot prove that this robot will not do anything crazy, but statistically it doesn't kill people around. So.
Yeah. So I know at some point that there was a like precisely transition from one to another. But there is also this thing, you know, like that's another how I would say. So basically, like one meta open problem in machine learning is to like transfer it from like academic settings to practical settings, right? So of course many of these things are already used, right? And like search engines and like all the things we discussed today, right? But many other things, they just happen within the labs, and basically like deploying them in like real environments, it's like either infeasible or undesirable, or no one like has any resources to do it. So that includes like precisely robots, like self-driving cars and stuff like that. So I think like commercializing these things and making them actually like practically feasible and useful for people, that's something where like this is like a big big discoveries are about to be made. Yeah.
But okay, but
I think I see that there is some nice progress on reinforcement learning. So in the group of Vetrov, so they have like one big problem that they use to compare algorithms, and there they made general purpose algorithms, so that does not take into account the differential equations to control a robot, and they outperformed. So it is general algorithm specific algorithms that were
what is the benchmark?
The benchmark is some so there is a bunch of robots from very simple with like 3 engines, and then there are more complex with 40 engines, and so you have to tell how much pressure every engine should produce, or torque, or whatever, and then the question is how fast can you make the robot move. And the most complex is a humanoid-like robot with arms and legs, and the robot should walk without falling. And in this they got like 50% to 20% speed improvement, and it's
speed of what? I don't understand. So
the target is to walk along a certain direction. And then people present these algorithms, and you see humanoid robots who walk like disabled people. It's very bad current situation. But now algorithms appear where you see like only very little disabled people walking.
Yeah, okay, but what was the learning? They used people moving, or what they used for learning? So what is the role of learning in this?
They use a setting of reinforcement learning. So they start with random things happening in the engines and see how their reaction improves to the desirable. So by making random moves, they see whether there is a progress towards their goal.
Oh,
and then
so they don't imitate any human actions. It's just an optimization in itself.
Yeah. and it learns, and they use techniques from machine learning to fit very good distributions toward so they try to fit the probability space of what are possible actions and what are possible future rewards and future states of the machine, and then they use all their machinery to fit probability distributions.
And but they are actual robots. So the benchmark.
No, it's simulated robot. So there's differential equations. They're simulated robots.
And it's essential, or you can do this with the real thing. For example, there is this Boston Dynamics things. There's dogs which run reasonably fast, and they can be kicked, and then they fall and got back, or they don't fall. So this is the same class of devices, or something different.
So they're simulated devices. I guess they're similar like them, like this. I don't know these Boston dogs, but
you it's very well known that you can see video in YouTube when
but I guess as long as they have at most 40 engines or something, you can apply these algorithms. And at some point, they will also use neural networks to model certain distributions. I mean, just 2 days ago, there was a big talk which I attended about this. But it's all I know.
And for example, about this, there was an extremely old paper of I don't know, 60s or maybe beginning of 70s. So there was a kind of natural language interface to a robot who or a model of a robot who makes some operations with some polyhedron. So they can say, please put the red cube on top of the green one, or get the same cube away, or something like this. So there was a text interface, and the robot did whatever it was asked. And so there was a kind of natural language processing based on theory about language, on grammars, on this and that. And also this planning of movements. So what now all this is wrong, and you use learning both for language processing and for movements, or it's still old style thing is needed.
I know very little, but I do know, again, at HSC, there are several competing approaches. So people do, I don't know what means old style, but there are people.
A book of Terry Winograd of 60s or 70s. They just use kind of context-free grammar for natural language. They have some logical intermediate language when to decide what is by move this cube, or red cube, or the biggest cube, or some kind of analyzing this logically. So
yeah,
now,
1 month ago, I attended the talk, and they kind of upgraded the logic. They go to something that looks like higher order. So there was a guy presenting a system. So there are several tasks in what you're saying. So you need to interpret images. You need to understand the question. So you need some language processing. And for language processing, it looks like they do now more advanced things and context-free grammars. And the guy presented something that looks like higher order logic, but I asked whether it was
it's
equal.
not related to machine learning.
They didn't use machine learning, but I guess some people do, because there exists a field of neurosymbolic neural processing, but I haven't read any paper about this.
One another big open question, it's related to what Bruno is saying, is basically use learning precisely for this neurosymbolic things, learn how to find theorem proofs, for example, right? It's a meaningful task that you might hope to try to solve, and why not to use learning? It's precisely what our brain is learning to do, right, when we learn mathematics. And I think there precisely the hard part is to combine gradient descent with logic inference. And for that there are like very limited progress. Like so, like I've seen some also talks on that and looked at some papers, but they like it's like very very primitive at this point. And also another area that would benefit from it is like learn to program. So for example, can we train neural net to write a program, or like given some input output examples, write some like as simple as possible program that transforms given input to given output. And again, like we have at Microsoft there is a group of people that does that, and they're like very good, but even state of the art there is like pretty dismal, so they can do barely anything. So but basically combining this as we call them like classic or like old school or whatever methods with like this let's call like differentiable approaches, like gradient descent more or less. That's something that people actively work on, and this is where like the progress is being made now.
But it's being made, but not made yet.
Not made yet, definitely not. Like they can write a program consisting of 3 lines. I think that's their limit. Yeah, and so basically, yeah, it's, and for proofs, it's also like ridiculously primitive. But I mean, yeah, there is no indication that the progress will not happen tomorrow.
But for language translation, it's more or less now machine learning is the best.
It's purely machine learning. It's like it's even like it's like they feed in like in the model like characters one by one, and it spits out characters one by one. It's like pretty impressive actually. Yeah.
And imagine the more similar task. You have an English text, and then you ask, I don't know, a Russian question. And you should say yes or no.
Oh, I mean, like even if both question and text are in English, this is like very hard. This is also like people work a lot on this. Again, like in the lab, we have a few people that do more or less that. Basically, it's like test taking. For example, you can ask like to neural network to try to like answer SAT test or whatever, like GRE test or TOEFL or whatever, right? And it's like, again, the progress is happening, but like it's still not good. It's like worse than like children or something, significantly. And it again has it's like this tension between like statistical nature of text. We can like understand that 2 words are similar just because they appear in similar contexts. That's like easy to do, right, computationally. But for example, even if you want to like keep track of all the negations and understand the logic structure of text, that's like something that is not known how to do well. And that's precisely where like people hope to use these like old school methods. And I don't want to call them old school. They're not old school. Like let's call them classic methods and this modern statistical based methods.
Yeah, it's like French for me. I can hear some words and I even understand that these words are related to some topics. But whether they want to.
Yeah, so you are at the level of state of the art neural network, probably. Yeah.
Yeah.
Yeah. There is
some yes, no, best algorithm beat human.
Yeah, but what are these best algorithms? Are these neural networks?
But let's see what are the benchmark also. You can even.
Because like there was this at IBM, there was this like IBM Watson that played Jeopardy. I think it had nothing to do with neural networks. They pretty much like just like hard-coded bunch of rules there, and it was good. It was beating humans. Jeopardy. It's like своя игра.
But what was? They ask some I don't know, some question. And
yeah, they ask trivia questions basically. Like whoever hits the button first can answer and like win some money.
So the question is just what is the third planet?
No. I mean it's more like no. It's most like. It can be about some like celebrities. It can be some like cultural thing. It's like it's not just like like questions about nature. It's like but it's like trivia, literally trivia. I don't know if you.
But they are in
natural language. Yeah. They're natural language questions, and you are supposed to like just produce an answer. So, like, I mean, it's a little bit more convoluted, but yeah.
Yeah, Nish, Degtyarev, if you are here, maybe you can say something. What is this? What is the kind of benchmark? What an example? What they do or whatever? You say that there is some benchmark when the machine learning beats humans, but can you give an example?
Right now, Misha Degtyarev cannot say anything because he is logged in with the option only here without microphone.
And you cannot relog with the proper way. Окей, если невозможно, ладно, но no, there is. I tried this reference, and there is a benchmark which says that this but they don't say any example of what are the questions. So probably it's somewhere.
Yeah, in my experience, you need to approach again. I have no idea about this benchmark. It might very well be very meaningful and a reasonable one. But when someone says that machine learning beats humans, you need to examine very carefully what it exactly means. Like what kind of questions is this? Like, for example, there is this classic image classification problem called ImageNet. It's basically just big data set of 200,000 images, and they also claim that we beat human performance. But the reason why they were able to beat human performance is because the classification, you need to classify each image belonging to several thousand classes, and we just can't keep several thousand classes in their head. So yes, sure, you can beat a human, but it's in some sense almost meaningless statement. But again, in this case, I don't know what this means. But this field tends to be a little bit sensationalistic, and you need to each such claim you need to actually if you really care about it, you need to understand it very well. So. But again, it might very well be in this specific case meaningful.
Our question, is France the same time zone as the UK?
I see. Okay.
I cannot believe that you can, by machine learning, you can somehow summarize this. Unbelievable. Can you see this example?
Yes.
But how it's really possible that one can read this text, but the French government canceled the decision? You can. Fantastic. If it's true, it's fantastic, really. But for another kind of
but I disagree that it's fantastic, because what these algorithms do, they more or less understand the sentences, and I don't know the specific algorithm, but I've seen such talks, and they just pick words from the sentence, use this BERT or whatever word to vec program, and then without understanding the sentences, they try to match to some sentences on the internet or whatever encyclopedia, and then they look around to pick up the answer and provide it. And if it's so,
this time zone is a special difficulty. Imagine there is a Russian sentence that Medvedev все ввел летнее время, а потом Putin все отменил. How can you cannot hope that it's.
Yeah, but also, guys, you should also understand that Misha pasted some examples from their README, so it's heavily cherry picked. It's okay. If you start if you start examining actual questions, their system answers, again, I'm sure it's good, but I would not be surprised that it makes some silly mistakes, in the example as you, Sasha, say, for example. So
yeah.
So of course it is impressive that it can do even these specific examples, but again, there is a big difference between what's the best performance it can achieve versus what's the typical performance and what's the worst case, right? So,
right.
Yeah. Actually, I kind of need to go soon. So, but what's the agenda?
No, no. First, I think that it's very nice experiment, and you will not be released completely, and we will ask you again at some other point on some other topic which will be specified later. So it's very nice that you are, as soon as you get the tablet for writing formulas.
Actually, it just got delivered, so yes, I can write formulas now. So.
Yeah. So that's exactly what is the only thing what was missing is this one. So,
Yeah.
but for now, I think we should finish because it's more or less 2 hours.